All right, 3.5 is maybe one of the most important sections that we're talking about this year. It's actually kind of easy, okay, but it is a topic that we use over and over and over, principles that we use, several principles that we use over and over and over throughout other sections, so it's very, very, very important. So we're talking about angles and triangles. Today we'll talk about how we can name triangles, and then some kind of new definitions for particular parts of triangles that maybe you haven't seen in the past, and how they reference and how we create them based off of other things, other angles, and ultimately in the triangle. So this is 3.5. The first thing we have to cover, because a main theorem that comes in this section is something that you know from maybe 6th grade, 7th grade, 8th grade, and we've used it a couple times in this class already. But in order to be able to prove that theorem, we need to have this postulate. We can't prove this. I'm going to give you kind of a visual, and maybe you can argue that it is true. But it says through a point, not on a line. Okay? So point P here is our point, and it's not on line L. Line L is the one that they're talking about. It says there is one and only one line parallel to the given line. What I don't like about this picture is that you can't see kind of a formation of what was the line that they were talking about. Say when it says not on a line, they're referencing line L. So what I want to do, I'm going to GeoGebra, kind of set this up for you, and hopefully you can get a visual of what's going on. We've got point, let's rename it here so that it matches up with what they were calling that, and we'll call this line L. Okay, so we got line L, and we got some point P that is not on line L. Okay, and right now I'll just unhighlight those so you just see point P. And P could be anywhere. It could be as close to line L as we want it to be. It could be on as far away as we want it to be. Okay, zoom out as far as we can and move that thing all the way over here. And it could be on this side of L. It does not matter where P is, as long as it's not there, right? Okay, because that would mean it is on L, and that would be a problem. So we just have point P over here. What the postulate is saying is that there is one and only one line that goes through there, and kind of give you the visual here of what we're talking about. That line right there obviously is not parallel to the given line, right? When I say the given line, I'm talking about the one that you started with, the one that was in the hypothesis, and that's the black one. And if I start to move this line and alter that red line, okay, we're still going to intersect out here, right? And I keep moving it, keep adjusting it, but I'm still start to see that's still going to intersect, right? Okay. Eventually, though, I should be able to align A so that maybe they don't. Can I get there? No. Okay, even that one, that looks parallel, right? But if I zoom out far enough, you're starting to see that's going to intersect down here somewhere, correct? Okay. What is being said here is that there is one and only one line, this red line, that is going to go through P and be parallel to that black line, and that line there is now that, come on, that red line, okay, goes through P and is parallel to this black given line. Does that kind of make sense? And you see that doesn't matter where P is. P could be here, and we highlight that one line that is parallel to the given line through P, okay? Once I transition B and move that, okay, move my line L, no matter how it was provided, how it was given to me, the red line adjusts and is parallel to. But that's the one and only one line that does that, okay? Now, why is this important to us? Why is this useful? It's because of one of the facts that is directly related to that, or that develops from that. I'm going to do this. I'm going to put another point down here on this given line. And now I'm going to take and do that. Okay? What kind of shape did I just create? Triangle. Okay? And we want to find out one of the main most important features about any triangle. Okay, and it's going to exist regardless of what the triangle looks like. If we, let me start coloring here a little bit. If I look at that angle right there, that angle right there, and that angle right there, what are those three angles going to add up to? 180. Okay? What is the relationship? Because the red line and the black line you know to be parallel, right? What is the relationship between that yellow angle and that yellow angle? They're alternate interior, so they should be what's one? Congruent. They should be the same. What about this purple angle compared to that purple angle? Same thing, alternate interior, right? Now you told me that these three angles add up to 180, right? Well, so the yellow one plus the blue one plus the purple one adds up to 180. So then a yellow one, a blue one, and a purple one in any combination should add up to 180 as well, right? So does that make sense that that angle there plus that angle there plus that angle there should also add up to 180? All right? And that's actually kind of like a geometric proof of why in any triangle there's 180 degrees in the three angles when we add them together. Does that make sense? Okay. I don't know if you guys have seen this before in other classes, maybe in 8th grade, 7th grade, whatever. If I take a triangle, okay, 180 degrees in that triangle, right? Kind of a verification that that's true. Take off an angle. Take off another angle. Take off the third angle, right? Take those angles and line them together, you should get a straight line. Does that make sense? Okay? So that tells us that those angles, peeling them away from this triangle, peel this one off here and put it right there. Peel, or leave that one, I guess, where it's at. Peel that one off and put it right there. You will always develop that straight line. So the three angles in a triangle always add up to 180. Okay? And that's regardless of the triangle. Okay? I've got a kind of an applet over here. Just created a general triangle. And I asked GeoGebra to basically add the three green angles together. And you're seeing those three angles being added together right there. Okay? That's the... over here, we see that one angle is called alpha, one's called beta, one's called gamma. If I highlight this, it's showing you, come on. Should show you the formula that I have in the background. There you go. Alpha plus beta plus gamma. So it's allowed to change. But as I move those angles and alpha, beta, and gamma all change, what is maintained with that number right there? It always stays the same, doesn't it? Okay. And you could see that maybe if we do it this way. We'll go, let's see here, alpha plus object, beta plus object, gamma, and then see what that is equal to, which is that one. Okay, and we can actually see then the components of those three angles as they change. Does that 180 ever change? No. But the component, if you take your calculator, add those together, you're going to get 180. Okay? Take those together, you're going to get 180. Okay? So no matter what the triangle looks like, three angles on the inside are going to have to 180. Okay? Now I want to go through a proof for this. But the proof is going to, the first step of the proof involves knowing this. And knowing that that line, that red line there exists to get us through the proof. We're talking about just kind of showing you what the theorem, what we call this, and we call it the triangle angle sum theorem. And it basically says the three angles of the triangle, three interior angles, the inside angles, at 180. It is something that when I say the angles of a triangle, I'm referring to the ones on the inside. because there will be some on the outside that you don't see right now in those pictures that we will talk about. Okay? So when I say the angles of a triangle, they're the ones on the inside. In order to do this proof, we need to know what auxiliary means. Anybody know what auxiliary means? Usually you think about it with your phone, don't you? Your aux cord, right? Auxiliary means extra. If you've ever been to like a college campus or even some big high schools, like Lima Senior has them, I don't know, I think even Walpock has some auxiliary gymnasiums where it's just an extra gym. It's just, there's no bleachers in it or anything. It's just an extra gym to do practices in. And on the wall usually says, it's Lima Senior's auxiliary gym or whatever. Okay? Just means it's an extra gym. Okay? Auxiliary cord is a cord that you're going to plug into your phone and then to your speaker or to your radio or whatever, right? Okay? Well, that allows you to attach an extra device to your radio or an extra device to your speaker. So auxiliary means extra. Okay? When we talk about auxiliary lines, we want they're extra lines. They're simply lines that we're going to add to our picture in our proof to help us maybe make some connections, make some links. Okay. So what we're going to do in the next proof is going to set up kind of looking like this. Here at the bottom, we are going to know we're going to start with a triangle. Okay, a triangle ABC, and we know that there should be a line that goes through B because B is a point that is not on AC, right? So there should be one point B, okay, that is not on AC, and there should be one line that goes through B that is parallel to AC. Does that kind of make sense? Okay. And now we're going to do it with B, but we could have done the same thing. Is A not on that line? So there's going to be one line that goes through A that is parallel to BC, right? Okay. And then likewise, we could do the same thing for C. C is not on AB, so there's going to be one line parallel to AB that goes through C. But we're going to start with this picture here and understand that red line does exist. Okay. And it's useful to have that in our proof here. Okay. I didn't reset this from last class. So when we do this proof, okay, I'll give you a couple seconds here, a couple minutes, I guess, to kind of start writing down the given in the picture. When we kind of look at this proof, the parallel postulate that we talked about at the beginning in slide 2 does exist, because if we got this line AC and point B is not on that line, there exists for certain a line that goes through B that is parallel to AC. We've just now highlighted that line, because highlighting that line, putting it in our picture, is going to produce some important information for us, some important connections and relationships. Here, the parallel postulate tells us it exists, and that it exists in a specific important manner in which that it's parallel to AC. But there will be times when we add auxiliary lines that may not be because of some postulate, some parallel line postulate. For instance, eventually we will look at like isosceles triangles, and we will want to prove something about isosceles triangles. So what we'll do is we'll create that line. Okay? It's an auxiliary line, but there's also another statement that goes along with it that says from any point not on the line, there is one perpendicular line to that given line. Okay? So there will be different reasons why maybe we can use an auxiliary line. And those different reasons will maybe provide us some relationships with that auxiliary line and other lines inside the picture. Okay? The reason I talk about it, some textbooks, some articles, PDFs, whatever you get out of online stuff, my videos, that kind of stuff, might not put this phrase in there. They might just say auxiliary line. Okay? But we have the ability to say, it's a little bit more than just an auxiliary line. It's an important auxiliary line that involves a feature of being parallel. The next statement they said is that they take and say that angle PBC plus angle 3 are supplementary. If I look at PBC, it's that angle right there, and I look at angle 3, it's going to be that angle right there, right? Why are they supplementary?
Because they're all line.
Yeah, they form that line, right? And you were going to say they're a linear pair, correct?
Yeah.
All right. So we recognize that visually those things form a linear pair. And we know by the linear pair postulate that linear pairs are supplementary. And that's, I've got written out what the linear pair postulate actually says instead of identifying it by its name. This is the actual phrase for that. Okay. So what we've done is, given the information of a triangle that's pretty basic, pretty non-informative, we add this, and that creates something with our picture that we can justify. We can argue. We know for certain now that we have PBC plus 3 is equal to 180. That would not have happened if I would have just left it as triangle ABC. I need that auxiliary line to develop those supplementary angles. Does that make sense? So that was the necessity of that auxiliary line. We just introduced the word supplementary, right? So it's probably a good idea to talk about what that means for us. And we do that in line 3 here. It says PBC plus 3 equals 180. And that is what reason? What of supplementary, though? Definition. Okay. So definition of supplementary angles. Okay. So those 3 statements come from using that that additional parallel line that we knew existed. Okay. Statement 4 actually does the same thing, but these 3 were kind of linked together. Statement 4 is kind of independent of anything. Okay. If I look at statement 4 says take this angle 1 here. Let me use this. If I take angle 1 and add to it angle 2, does that give me the red angle, PBC? Okay. So what allows me to take 2 angles, add them together, and get a larger angle? Say again? Angle what postulate? What are you doing with them? Angle addition. Okay. So PBC is equal to 1 plus 2. That's your angle addition postulate. Okay. So now what's nice is that this statement here, 4 and 1, 2, and 3, I guess 2, 3, and 4, statements 2, 3, and 4, dependent on having statement number 1, right? Without number 1, statements 2, 3, and 4 cannot occur. Okay? So 2, 3, and 4 have to come after 1, but this statement number 4 could have kind of bounced around, and it could have came there, could have came between 2 and 3, it could have came there between 1 and 2. It's kind of independent of the other statements up there already. Does that kind of make sense? So you might, at some point, do a proof that's a little bit different than somebody else's based on your dependency or independency of statements. However, statement 5 is dependent on those 4. So statement 5 has to be made after the first 4 are made. And kind of look at what's going on here. I see and think that looking at that statement right there, because it's an equation with 180 in it, right? It's pretty similar to that one because it's an equation with 180 in it, right? Okay. And it's even more similar because we have 3 equal to 180 there, or something plus 3 equals 180. And over here we've got something plus 3 equal to 180, right? So those purple parts are the same. But these yellow parts that remained are different, right? But what did we say in step 4? Yeah, we said angle addition. Said PBC was the same thing as 1 plus 2, right? So step 3 and 4, step 3 and 5. 3 and 5, do you guys recognize that those are the same thing? Except for instead of writing PBC, we've written 1 plus 2 because they are the same thing. We define that in step 4. So what is that, Cameron? Substitution. Okay? So a substitution property. So now, 1 plus 2 plus 3. We're showing that these 3 angles up here add up to 180, right? And that's something that we knew visually, but we had to prove it using geometry, regardless of what those individual angle measurements are. Right now they're arbitrary. Measure angle 1, measure angle 2, measure angle 3. But no matter what they are, this one's 20, this one's 30, this one's 150. Okay, that doesn't matter. Add up. 20, 30. 130, okay? Or 10, 10, and 160, okay? We're saying that it's regardless of those three measurements, they're going to add to 180. Does that make sense? Okay? Now we come down here and we look at statement number 6. And statement number 6 is dependent on statement number 1. The key thing that we said in statement number 1 was that there's parallel lines, right? What is the argument about angle 1 and angle A that you told me earlier when we looked at it with this picture here? You told me these yellow angles, right? Okay, what were those yellow angles? Alternate interior. You said they were congruent, right? So that's why we're saying 1 and A are congruent here. They're alternate interior. What about 3 and C? That angle there and that angle there, they're alternate interior as well, right? Okay. So 3 and C are congruent because if parallel lines are cut by a transversal, then alternate interior angles are congruent. What allows you to go from congruency straight to equality? Those phrases really aren't much different, right? We just took the congruent sign out, put the equal signs in, right? You remember what that was? The definition of congruency, okay? And this is actually the phrasing in the book that you would see in the glossary when you looked up congruency, okay? Congruent angles have equal measures, or in the glossary it might even say congruent segments have equal measurements. Just in this case, we're talking about angles. So now, let's think about this. We now know 1 is the same thing as A, right? So 5 and 8 are the same statement. But where I saw 1 and 5, I'm going to replace it with A, because they're the same thing. Does that make sense? So I replace 1 with A. 2 doesn't change. 2 in this line up here in 5 is the same as the 2 down there. Okay? Now up in line 5, we had then measure of angle 3 at the end, but we just talked about how 3 is the same thing as C, right? So I take 3 out and replace it with C, and we got A plus 2. So A is that angle, 2 is that angle, and C is that angle. And we're saying that those three angles, which are the interior angles of a triangle, should add up to 180. All right? So we've proven what we were trying to prove, that the interior angles of a triangle add up to 180, and that property is just a substitution property. Okay? But what's nice about that is now we know, regardless of the triangle you deal with, you will always have 180 degrees in the sum of the three angles. All right? And it's important to be able to prove that, but it's also important to remember that we're going to use that fact an endless amount of times this year to not only deal with triangles, but to deal with other shapes. Okay? Because later on, I might ask you, how many degrees are there in, just see here, let's say that I ask you, look at this shape there, and I ask you, how many degrees are there in those where we got 5 angles? Well, because we have the ability to take that shape and kind of chunk it up into what other shapes? Triangles. Okay. We should be able to take 180 plus 180 plus 180. Now I know how many degrees are in that triangle. What? I'll get it in a little bit. Sorry. So learning something about triangles is going to eventually lead us to something about this figure. Okay. And then it'll lead us to other figures that might be much more complicated. Let's say you may know what a 12-sided figure is called?
Decagon.
Close. Decagon is 10. 12 is a dodecagon. If I get that, come on, zoom out. Come on, we get that shape right there. Okay? But what we learned about that shape is because of what we just learned about triangles. Okay? Yeah, it looks like an octagon's at 8 sides, right?
Yeah.
Triangle, by definition, we haven't really talked too much about other vocab words like polygon or closed figure or anything like that. So I don't want to define a triangle using those terms, because then we have to define those terms right now. So let's just call a triangle a figure formed by 3 segments joining 3 non-collinear points. Okay? 3 segments joining 3 non-collinear points. Be a vocab word that you guys see on the test. Some things that you guys know based on triangles, and we want to name and classify these things, talk about them. We can name triangles based off of the amount of congruent sides they have. We can name them based off of the types of angles that they have inside them. And then we can also kind of maybe merge those together and talk about them based off congruent sides and angles. Okay, so you've probably seen these before. Scalene means no congruent sides. Isosceles means at least 2 sides congruent, so that's important. That key phrase, at least. So if I have 3 sides congruent, is that still isosceles?
No.
It meets the requirement. At least means bare minimum. So if I have 3, have I met the requirement of at least 2?
Yeah.
Yes. Okay. So isosceles is at least 2 sides congruent. Equilateral is all sides congruent, right? So by knowing this concept here, that phrase, at least, okay? Whenever I get an equilateral triangle, does it have at least 2 sides congruent? So an equilateral triangle is also what? It's also isosceles, okay? So throughout this course, we're going to learn things about that are special for isosceles triangles. We're going to learn things that are special for equilateral triangles, and knowing that every equilateral triangle is also isosceles is going to allow you to transfer some of those relationships to those shapes. Okay? But is equilateral is isosceles, but is every isosceles triangle equilateral? No, because if I have just 2 sides congruent, it's not equilateral. It's still isosceles, but it's not equilateral. So it's the idea, we've heard this before, is a square a rectangle or a rectangle a square, right? Same thing happens with isosceles and equilateral triangles. Is equilateral isosceles? You betcha every time, right? But is isosceles equilateral? No, not 100% of the time. Okay, unless that isosceles triangle for some reason has 3 congruent sides. Okay, we can name them based off of their angles, types of angles. Acute angles. You got 3 acute angles. It's an acute triangle. You got 1 obtuse angle. It's an obtuse triangle. Why can't you have 2 obtuse triangles? 2 angles. Be 1 over 180. Okay, the smallest obtuse angle plus the smallest obtuse angle is going to exceed 180 degrees, and you don't have enough then for that 3rd angle. Same idea with right angles. You can only have 1 right angle. Because if I have 2 right angles, I get to 180 and don't have anything left over for that 3rd angle, right? Okay. Equiangular, all angles are congruent. Okay. Equiangular means all angles are congruent. And for triangles, this is only true for triangles right now. If it's equilateral, it's also equiangular. And that's actually a kind of a 2-way street. If it's equiangular, it's equilateral. If it's equilateral, it's equiangular. Okay? But that is only true for triangles right now. Okay? Equilateral implies equiangular for triangles. Okay? But think about these rectangles, these chalkboard rectangles right here. Okay? Not triangles, right? Okay? If I ask you about the angles, what are all the angles in those rectangles? 90. So it's equiangular, right? But is it equilateral? No, these triangles, these sides of this rectangle are different, right? Okay. So for other shapes, equiangular does not always mean equilateral. Does that make sense? Okay. In a square, it does. Okay, but in a rectangle, maybe that doesn't happen. Yes.
So if it's equiangular, then it's also isosceles.
Yes. Because if it's equiangular, it's equilateral. If it's equilateral, it has met the fact of being isosceles as well. And you start to see kind of the headache that you kind of create when you start classifying things, right? And start having to develop and understand the relationships between things. These statements are called corollaries. And you don't really need to know what statements are corollaries and what ones are theorems and that kind of stuff. But basically, a corollary is simply a statement that follows directly from a theorem and can be easily proven using that theorem. Okay? And the theorem that we're going to use is this one here. Okay, the sum of the measures and angles of triangles 180. Something we've proven, something we know. If we start, I'm going to start down here at this one here. Would it be easy to prove that statement by knowing that if it's an equiangular, that means all 3 angles are the same, right? And if they need to add to 180, can't I find one of them by taking 180 divided by 3 and getting 60? Does that make sense? Okay. So that statement, each angle of an equiangular triangle has a measure of 60 degrees, is easily proven from the use of this theorem up here. Okay? That's why it's called a corollary. something that's on there, and if it's equiangular, it's also equilateral, right, for triangles? So every angle in equilateral triangle is also what? If it's equiangular, it's equilateral, right? And equiangular just said that they're 60 degrees, right? Well, in equilateral, they all got to be what? 60 degrees as well. Okay. Two angles of one triangle are congruent to two angles of another triangle, and the third angles are congruent. Think about this. If I give you, let's see here. Try to make this kind of as easy as we can with these. There we go. All right. Let's do it this way. All right, so if we look at those two triangles, we know that the angle, get it backwards. The angle there, come on, is 90 degrees, right? If I look at that angle there, it's 51.34, right? We have the angles of one triangle. That angle and that angle are congruent. That angle and that angle are congruent, right? What's that tell you then about that angle compared to that one? They have to be congruent. That's called the third angle theorem. Hopefully that's pretty obvious. If I take 180 and minus 90 and minus 51.34, and I get a measurement right there for that angle, whatever that is, okay? And I do then the same thing over here. Well, I better subtract 180 or 90 and 51.34 the same way from that 180 that I did the first time, right? Okay? 180 minus 90 minus 51.34 is the same no matter how many times I do it. So if I do it once, I get a measurement here. Do it again, I get the measurement here. The relationship that you would see then between those two angles is that they're the same. And if we ask it, that one is up 38.66. And that one ends up being 38.66 as well. Okay? And that is maintained no matter what we do. If I can try to get that, I'm not going to be able to do it. Let's do it this way. Wow, I messed up. But if I could make that one 42.27, you would see at that angle there, which is 33.69. That one is 104.4. Make this one 104.4. These angles down here would still be the same. Okay? If you know two angles of one triangle congruent to two angles of another triangle, third angles have to be congruent. Third angles theorem is a very, very, very useful tool for the rest of the year. If I have two angles that are acute in a right triangle, okay, so I got a right triangle here. Okay, there's my right triangle, right? These are the acute angles. What's 45 plus 45? 90. If I do it this way, what is 51.34 plus 38.66? 90. The acute angles add up to 90. And that's what complementary means, right? So those are all features that we're going to use throughout the course that become very important. Exterior angles. This is talking about the additional angles that I talked about in a triangle that are useful to deal with. An exterior angle is simply when you go from that point there and you travel to another vertex, but travel beyond that vertex and extend that ray. The exterior angle is the outside angle that's created. Okay? Would you guys agree that that angle right there is attached to it? You agree that the red angle is attached to the exterior angle? They're linear pairs, right? Okay. The other two angles that I've got those arrows to are referred to as remote interior. That is a remote interior, and that is a remote interior. Okay, what's the word remote mean? Okay, so you got the remote control, right? And so you're laying on the couch and you're controlling TV from a distance, right? From far away, right? Okay. You're separated, you're not tethered to the TV, right? So when we talk about remote interior, that word remote for us means it's an angle that's far away from the exterior angle. Or that's separate. Somebody in the last class said separate. I like that idea because this one's attached, right? Those two are attached. These two are separate from the exterior angle. Okay? So we call them remote interior angles. Now there's a cool feature about remote interior angles because let's say I give you just arbitrary values here. Let's say that's 30. Let's say that's 50. What would this angle here have to be for the triangle?
10.
Careful. What do all these have to add up to?
180.
180. So if I've got 80 already, what's this one got to be?
100.
100. If those two are a linear pair, what is this one got to be?
80.
80. What's the length that you just discovered then about that angle compared to the remote interiors? What can you do with the remote interiors to get that exterior angle? Add them together, right? 50 plus 30 gives you 80, right? Okay. So what we come up with is another theorem that says the measures of an exterior angle, or the measure of an exterior angle, is equivalent to the sum of the two remote interior angles. So here we're seeing the measure of angle 1 is equal to 2 plus 3. Okay? If we look at GeoGebra real quick, see where I had it. Is this one? If I put in an exterior angle, so I need to attach a ray, so my exterior angle ends up being this angle right here, and it ends up being that one, 128.11. Come over here, these two are the remote from that. 61.67 and 66.44 adds up to 128. Does that make sense? Okay. What is kind of neat is, that's one exterior angle. If I start at A and go through P, A through P creates that exterior angle. And then if I go through P through B, it's going to create that ray and this exterior angle here, which is that one. Okay. So those are the three exterior angles that we talk about for a triangle. Notice that, 113.56 is 51.89 plus 61.67. That will give me that 153.56. Okay. Now, this here is those three orange angles added together. It's kind of a unique value, isn't it? Okay. 360. Now, no matter what those orange angles become, what happens to that 360? Anything happen to that 360? Stays 360, right? Even though those orange angles, those orange exterior angles individually change, they still add up to 360 no matter where they're at. Okay? So that's a kind of a property that's very useful for some of the stuff that we do. All right, so give you a couple examples before we get out of here. What can we do with that 5x to come up with a relation to solve for x? What kind of angle is that 5x? 5x is that angle out there. What argument can you make about it? What's 5x equal to, guys? X plus 120, right? Okay. That's an exterior angle. And this is a remote interior. And this is a remote interior. So add the remote interiors together and set them equal to your exterior. Okay. You can solve that. I'll let you solve that on your own. You can then find the individual angles there for that. If I go to this one, okay. This one's incorporating parallel lines, right? Okay. Usually when they give you parallel lines, you're probably going to want to use those. So if I look at that parallel line, that transversal, what can you tell me? X is 30, right? Okay. They're alternate interior. So now let's look at this. Let's look at that triangle. Do you know if you got two angles of the triangle, do you automatically know the third one? What's that third angle got to be? 100, right? Do you now know what y has got to be? What's y got to be? 80? Do you now know what this has got to be? 100. Why?
Vertical.
Okay, it's vertical. Is it also supplementary here?
Yeah.
Okay. What does this angle got to be then?
50.
50. Why? Okay, it's alternate interior with that 50. But if I know these two, don't all three of these have that up to 180?
Yep.
So you're starting to see that when I come up with a conclusion about something, there might be 3 or 4 other reasons that verify that conclusion, right? Okay? And that's kind of the nice thing about some of the problems that we go through in this course, is that if I start to learn my properties and understand my properties pretty well, I should be able to do the problem one way, get an answer, go back through the problem a separate or second completely different way, and get the same answer. If I get the same answer, it tells me my first way was probably right? All right? And it's kind of built-in checks that kind of help, as long as we know all our properties and our theorems and that kind of stuff, okay? You're going to see in your homework this evening questions, and we'll continue to work on this in the next couple of days, where you'll see questions kind of varying. This one's a little bit more complicated. You'll see one like this in your homework, I believe. Take your time, draw pictures, make connections that you understand, highlight things, redraw the pictures again. It's going to make things a lot easier on yourself, okay? But the number one thing that you need to learn from this section, 180 degrees in a triangle, okay? If you got that, I think you'll be pretty successful for the next couple weeks, all right? You can get out of here. See ya. Have a great day.